Welcome to the solutions to the circular and planetary motion problem set. Problems numbers 1, 2, and 3. Number 1, if a car's wheels are replaced with wheels of greater diameter, will the reading of the speedometer change? Explain. Let's suppose the picture here on the left, and these are bike tires, but it doesn't matter, just for representation. I like this one because you can see the axles here. Let's suppose the picture on the left is the wheel that the factory, when they designed the vehicle, this is the radius of the wheel that was intended for the vehicle. All speedometers are preset at the factory to match up to the intended radius of the tire that's normally put on the vehicle. What you have to keep in mind for comparison's sake here is that the axle in both these cases is going to be spinning at the same speed. So if you're one of these rednecks that wants to put a lift kit on your truck or your car and then put bigger diameter tires on it, how would that impact the speedometer? Well, as you can see, if both of these wheels are turning at the same rate with regards to the axle, then out here on the diameter, if this covers a distance x, by turning the larger one at the same speed, it's going to cover a larger distance x. And you're going to cover that distance in the same amount of time. This is going to cause the speed of the vehicle to go up. So it's going to cause the speed to increase. However, the car still thinks it's basing that speed, the speedometer is preset based on the RPM and gear ratio in the transmission. So the speedometer is still going to read the same, but you're actually going to be going faster than what your speedometer says. So you need to be careful if you're one of these people that goes ahead and does that. Okay? All right, 2. Because of the Earth's rotation about its axis, you weigh slightly less at the equator than at the poles. Why? This diagram is a largely exaggerated picture of the oblate spheroid that is the Earth. And if we draw 2 dimensions here, both from the center of the Earth, one, the radius out to the center, and the other, the radius up to the North Pole, you clearly see that the distance from the Earth surface to the center of the Earth is much less. We'll call that one R1, we'll call this one R2. R1 is less than R2. Well, why would you weigh slightly less at the equator? Applying Newton's universal law of gravitation, which we're going to have a separate lesson on here later on, Fg, the force due to gravity acting on an object, is big G m1 m2 over r squared. Well, in this particular case, the force due to gravity is big G, mass of the Earth, mass of U, which we'll call a mass of object, at the surface of the Earth, and r squared, in this particular case, r normally represents the distance between the centers of the object. Well, in this particular case, it would be from the center of the Earth to the center of the object, which would be the radius of the Earth. Well, you can see that if R2 is greater than R1, so if we put R2 down in here, that's an increase in R, which then gets squared. And this would, of course, decrease the force due to gravity on the object. So you would weigh slightly less at the equator than at the poles because you are further away from the center of the Earth at the equator than you are at the pole. Your R value increases, therefore your force due to gravity at the equator decreases. Lastly, number 3, it has been suggested that rotating cylinders about 10 miles long and 5 miles wide in diameter be placed in space for colonies. The purpose of their rotation is to simulate gravity for the inhabitants. Explain the concept behind this proposal. I actually Googled images for this and was stunned to find this particular one right here, which I'm going to circle two parts here. Habitants in this part rotates for gravity, and somewhere down here, habitants in this part of the cylinder, and it's rotated for gravity. What's that all about? The way this works is actually not a centripetal force question, it is an inertia question. Because as the cylinder rotates, the tendency of the body is going to be to resist changes in that motion, and the body is, let's say it's you, the person, inside that cylinder is going to be always changing direction. Even though you may not realize it, with something this large, 5 miles in diameter, rotating, it wouldn't take much of a rotation for you to experience the necessary gravity, yet you would hardly feel like you're moving at all. Pretty neat concept that they're using here. They're using friction and inertia to simulate gravity. Friction keeping you against the surface, and inertia is your body's tendency to resist changes to your current state of motion, and you're always being the direction of your velocity is always changing, and you're being I don't want to use the word pushed because there's not a force acting on you. Your body wants to stay straight while the cylinder is rotating, so your inertia will keep you against the side of the container, simulating gravity. Obviously, how fast they spin the cylinder is going to determine how strong you feel that simulated gravity, because the faster they spin it, the greater your inertia is going to be. Okay? Over here on the right, we have another space colony model. Basically, it looks like a tire, a bike tire. And what they do is they spin this like this, and then the inhabitants are on the inside of this tube right here, and you can see that there would be inertia towards the outside of that tube, and you would experience gravity because of that rotation and your body's tendency to want to resist changes to that state of motion. All right, this will wrap it up for problems 1 through 3. We have 2 more conceptual questions we'll get to tomorrow when we cover numbers 4 and 5.